Ciao! Welcome back from the CAOS team at Politecnico di Milano. This video will guide you into a second example of usage of the CAOS framework. The demo application we are going to talk about regards Streaming Stencil Time Step, or SST. An SST is an electronic design automation of iterative stencil loop from plain C or C++. The SST relies on a mathematical framework, the polyhedral model, to model the ISL and extract the relevant feature, and no application design intervention is required. The hardware accelerator resulting from the EDA is a composition of independent modules that communicate over FIFO channels. Its feature is that it has a data flow computation, its bandwidth requirements are independent from the queue size, and it is almost linear in performance scaling. So, let's see how to design an SST on our framework. For this second example, the flow that the user needs to follow in order to use the framework is very similar to the one of the previous example. Let's start with a new project by importing the code archive for Jacobi. And then select the JSON file containing the program description and run the IR generation. As in the previous example, the CAOS framework is giving us a program static call graph and a list of identified functions that we can click and analyze. Then we can move in the next phase. For the applicability check, we need to provide the architecture description and select the architectural template that we want to use. After running the template's applicability check, the framework confirms that the master-slave paradigm is not supported, but the SST architecture template can be used for this application. For the profiling, we need to specify a name for the dataset. In this particular case, we do not need to select the dataset archive as the test is embedded in the source code. So, we just click Submit and start the profiling. As in the previous example, profiling information is given. For what concerns partitioning, we have just one function to choose if you want to implement it in hardware or in software, and it is the kernel Jacobi. So we check hardware and run the partitioning. The partitioning is complete, so we go in the next phase. We start with the stated code analysis that give us values regarding best, worst, and average latency for our kernel. At this point, we can run the hardware estimation. Here, we have an estimate of the hardware resource consumed by our kernel. In this particular example, our Jacobi kernel is consuming 8 VRAMs, 0 DSPs, 90 flip-flops, and 117 LUTs. Now the framework allows us to perform a performance estimation. Here we have different information. On the left, we find the current function implementation and an estimate of performance. In fact, The framework is telling us that with the current implementation, we should expect performance in the order of 12.68 seconds at a clock frequency of 200 MHz. While on the right, there is an estimate of performance for the optimization called enqueuing. With this optimization, we should expect performance in the order of 0.062 seconds at a clock frequency of 200 MHz, with an error consumption of 1,648 VRAMs, 0 DSPs, 18,540 flip-flops, and 24,102 LUTs. Now we can start with the code optimization phase. The result of this phase is a table, telling us on which kernel, hence on which function, the optimization has been applied. Finally, we can proceed with the generation of the IR. At this point, we have two different folders. The first one is showing the initial code that we just optimized, and the optimized version of this code is in the optimized folder. Now we can choose to select the optimized folder and start the optimization process again, or by clicking on the blue button, I can download a version of the optimized folder on my computer for further analysis. Otherwise, I can select the optimized folder, complete my function optimization phase, and start with implementation one. In this phase, the framework generates the bitstream and the HDF file in order to run our application on our FPGA board. The end of the implementation phase is stored in an implementation archive that we can download on our computer. By looking inside the folder that we just downloaded, we can see that there is the bitstream and the HDF file. So now we complete the implementation phase and the entire flow is completed. We can then just go into Project, save the current version, and finally close it. So, thanks for your attention from the CAOS team. If you need any further information, please do not hesitate to contact us.